Welcome, everyone. Welcome to another virtual science camp. So it's Saturday, January 23rd. Thank you for joining us. This one's going to be on modeling magnification. So remember, this winter, we're going through a series of particle physics ones. And hopefully by the end of this session, we'll see why we need particle accelerators to see the smallest things we can. So if you're just joining us, I recommend you put us into speaker view. That'll be in the top right of your screen. You can toggle between gallery and speaker view. When you put it into speaker view, you should actually see three screens because I have three things highlighted. There's me. For me, I'm in the bottom center, but for you, it might be different. And then you'll see Alex, who you'll probably recognize from a number of other sessions. And then we have a second Alex, which is for his microscope, because he's volunteered to lead off this session by showing a couple of things with his microscope, so we can get into looking at things that are smaller that we can see with the naked eye. And those are things that we still can see with the help of microscopes. After that, we'll get to things that are even smaller and smaller, and we'll be modeling how electron microscopes and eventually particle accelerators work, because we get to things that are too small to even see. But without further ado, I'll turn things over to Alex, and I'll turn off my spotlight from me. So thanks again for joining us, Alex. I'm excited to see what you're going to show us.
So hi guys, I'm going to show you a series of things. So the camera where you can see my face, I'm going to reverse it and show you the things from what a human can see. And then on the other Alex Hancock, you should be able to see the things that the microscope can see. So first of all is a really basic thing. It's just a carpet. So the carpet looks totally normal and flat. But as soon as I do this, you're going to see on my other screen, this is what a microscope can see. So this is my microscope aimed at the ground, and that's what the microscope can see instead of a carpet. So that's really cool. And you can move it around and see all the little strands of it. And just to give you an idea of how little those strands are, I'm going to put it against here. So the little dashes are separated by 0.1 millimeters. So that's how small it actually is. A second thing I'm going to show you is a piece of plastic. So I'm just going to put it onto my computer and focus it, which will take a bit of time. And oops. So I'm going to turn the lighting down a bit so that you can see it better. So here is the plastic and a little bit of the computer. So I'm going to show you this thing here, which is blue. And this is what you see through the microscope. So really, really tiny. Next, I'm going to show you what a screen is actually like. So here through my camera, you can see the Zoom session that we're on. And as soon as I put the microscope on it, oops, you can see all the little colors. So the screen is made out of lots of colors which are moving at once. So you can see the red, the blue, and the green normally. And I can get in even closer. And at the end, you should be able to see there. So this is what the screen is actually doing, and that is what you can actually see. So this is nearly 1,000 times bigger than what the human eye can see.
And there's a lot of cool stuff we can do with the primary colors of light, but the story behind that is probably left best till another camp.
Yep. So that's it there. Perfectly done. So next I'm going to do a piece of cardboard. So cardboard's basically a bit like wood, and it's made out of loads of tiny fibers which stick together and make this. So from the naked eye, you could not see all those little bits of dirt on it over here. I'm going to do it right here, this clean piece of it. And when we put it, we're going to see loads of dirtiness because the cardboard is actually really dirty, but it's microscopic bits of dirt that are attached to the fibers. And that I think is really cool because when you think something is clean, it never actually will be clean on the microscopic level. Next, I'm going to show you, basically the first microscope was kind of made in the principle of a bit around denim and clothes. So here's just a normal jeans from everyday life. And when I put the microscope onto it, you can see the tiny strands which pull together the jeans and make it what it is, denim. And you can see it isn't perfect. If you put your hands on your trousers, for example, you wouldn't actually think it was flat. But here you can see it's going all over the place. The strings everywhere. And so I can zoom backwards and backwards and backwards. But primarily, you can go up to 1,000 times with this microscope. It won't be very focused. See, this is 1,000 times. This must be around 900 times bigger. And you can see it perfectly. Finally, I'm going to show you something which is really scary to me. And it's really cool. So I'm going to let you try and guess. You can say in the chat what you think this is. I'll leave you a few minutes to write in the chat what you think this is through the microscope.
And we already have a guess from Deanne Rose. So she's guessing it's hair. Any other guesses? Oh, plastic fibers. It's true, it's got that shiny aspect. And Deanne Rose says she's 100% sure.
Well, she's right. It is hair.
So well done. I'm guessing, Deanne Rose, you probably have a microscope of your own to be so sure about that. Is that the case? No. Okay. And I guess that it's blonde hair. Alex, can you confirm the color of the hair?
So the color is actually brown. It's my hair, totally normal hair. And it's actually on me, yeah. So this is my hair right now. So if I turn my video of the camera around, you'll see I've got a microscope pointed at my head. And that is what you see through the microscope. Oopsie. There we are. And that is what you can see through here. So hair doesn't actually look like that. It looks like this to us. But when you look at it a bit better, you'll see all of this. So adults wouldn't really appreciate we did this to them because you'd see every single white hair stuck in the black hair. And so, yeah, that's the amazing things you can do with a microscope and how the naked eye of a human cannot see so amazingly all those things. And that's me done.
Excellent. That's been great. Thank you again for starting off this session and sharing those things down your microscope, Alex.
No problem. I'll leave on my phone and join on my computer.
Excellent. Sounds great. If you end up disconnecting, I'll let you back in from the waiting room.
It should work.
Perfect. Okay, so now we're going to look at how small some of those things were and what happens when we want to try and see something smaller. Because as Alex was saying, he got up to about 1,000 times magnification, and it turns out using light, we can't get all that much better than that. Like we can get a little bit better than that, and at some schools, and especially at universities, research facilities, they might get up to 1,600 times magnification, like 1,600, maybe a little bit better than that. But then we start running into some problems with the nature of light itself. So to try and organize how small things are, we're going to attempt an interactive activity using Padlet. It's the first time I've tried this in the context of a virtual science camp. So if it doesn't work well, don't worry, we'll abandon it and just go to something else. But I'm going to share a link with all of you in the chat. And I'm going to share the same thing on my screen. So if you're joining like from a phone and you're having a hard time switching between windows, don't worry about it. You'll get to see the Padlet on my screen. But once you have it open, you should be able to see there's names of a number of different things on there. And is my screen coming through okay? Like you can see a reddish orange screen with the title Modeling Magnification, right? Either by shouting out on your microphone or by writing in the chat, can you guys let me know if you managed to open the Padlet on your own device? Can anyone either confirm or deny whether you managed to open this as in a different window so that you can drag it around and play with it?
Yes, we managed to open it.
If you manage to open it, just grab some of the boxes and move them around so that we'll see, like if some move around without me touching them, it's functioning, it's interactive for you guys, and things are working. Nothing yet appears to be moving. If you manage to be able to drag and move things around, feel free to do that. Otherwise, shout out and tell me where to move some of these things. What we're going to try and do, you see a number of things listed on here, like scissors, alpha particle, coin, human red blood cell. And we want to try, using our prior knowledge as a group, to organize these things in terms of size. So the smallest things up near the top and going down in a messy type list, going to biggest things at the bottom. Does that make sense? So can someone shout out what some of the bigger things on this list might be? And either shout out, like with your mic.
Hydrogen atoms.
Hydrogen atoms, excellent. So that'll be on the small end of things. So hydrogen atom, I'm going to put all the way up at the top.
Can't move it. X-ray. X-rays.
X-rays, those are pretty small, so those are going near the top. Anything else that should go near the top?
Nucleus of gold atom.
Nucleus of gold atom, excellent.
Scissors.
I'm not seeing where I put that.
On up.
Oh, yeah, already pretty high. And coin is bigger than that, so I'll put it arbitrarily below. So these things are near the top. How about near the bottom so we free up room near the top? What are some of the biggest things on the list?
Biggest thing.
Hydrogen nucleus.
Scissors.
Scissors are pretty big. Human hands need to use the scissors. How about a whole human?
Yeah.
That's probably the biggest thing on the list.
Me.
Scissors.
Let's go with some more big things. After the human hand and scissors, what are the next biggest things?
Grain of sand.
Grain of sand.
Coin.
Grain of rice. Key. Scissors. They're 2 times scissors.
Oh, I'll delete one. There we go.
Grain of rice.
Grain of rice. And that's bigger than a grain of sand, right?
Human hair, maybe.
Human hair. Okay, and we saw that under Alex's microscope, so we got an appreciation of about how big that is. He also showed us pixels on a laptop.
Flower.
Particle of flour. Do we think that's bigger or smaller than the width of a human hair?
Smaller.
Maybe smaller, but we're not sure, so we'll keep it close. How about the pixels? We saw pixels on Alex's computer, right?
The most smallest.
Really
Those
small.
are pretty small, right? So we'll put it somewhere around here. Now we've got a whole bunch of things with light. We got to figure out how that fits into everything else. Oh, and some kind of cells like human blood cell, salmonella, coronavirus. Where should these fit in? Just shout out where you think some should go in relation to anything else.
It's hard. Oh, Mom. Pixels are microscopic.
Gamma rays just before X-ray. No, just after X-rays.
After like above or below?
Below.
Below? And it turns out X-rays are actually a little bit bigger than gamma rays.
Oh, okay.
But that's okay. It was a good guess. And you knew that they were pretty small, so they fit on there. How about light? Is ultraviolet light bigger or smaller than blue light?
Smaller, maybe.
Smaller. And that was a one or the other, so you had a 50-50 chance of getting it right. Blue and red. Any guesses?
Red is bigger, maybe, I think.
Red is bigger, yeah. Perfect. And how does all that relate to human red blood cells? Is that bigger than light or smaller than light?
Bigger.
It's bigger than
Than light? And probably smaller than hair, right?
Yeah.
And I'll bring some of these things down a little bit just so we have some more room. Okay, and we have most of this list most of the way in order, right? We're not really sure between human hair and particle of flour, but they're both pretty small. Pixel on laptop, do we think it should go above or below these?
Above.
Above, okay, so it's a bit smaller. Malaria parasite?
Above, maybe? I'm not sure.
Like around here? And does anyone know what malaria does? Like what is malaria?
It's yellow fever.
Well, it's similar to yellow fever, but it's not exactly the same thing. But the symptoms are similar as well as the range. So it's a disease, right?
Yeah.
And it's a disease that affects blood cells. It actually goes inside of human blood cells. So the parasite's got to be smaller. Although it depends what stage of life and what stage of development, because when it unravels, it's like a long string that's longer than a human red blood cell. But like we talk about when it's in its ball form, it's smaller and it fits in. Coronavirus.
Around the same thing, right?
What's that?
Isn't coronavirus like about the same thing as malaria parasite?
Oh, that's a good question. So coronavirus, and this comes up a lot when people talk about masks and pore sizes on masks and things like that. And it turns out viruses are actually a lot smaller than parasites and bacteria. I won't go into detail on this, but like parasites, they're eukaryotic cells, which means they're kind of similar to animal and plant cells. They're not that similar, but they've got to have like some basic size requirements to fit in that. So it's not like parasites generally aren't that much smaller than human cells. Whereas bacteria, they're about 10 times smaller, and viruses are even significantly smaller than that. And it turns out that viruses like the coronavirus, it's actually slightly smaller than blue light. So it's really small. And we'll get to why that's a problem for trying to look at it in just a minute. Hydrogen nucleus, that's near the hydrogen atom, but it's a part of it. The nucleus is the center part, so that should be smaller than the whole atom, right? And then the nucleus of the gold atom is smaller than the whole hydrogen atom. Alpha particle we'll put up there. And there's no room to have it like fully in order, but that's more or less our list of how small things are with these common things. Now, we saw Alex's microscope, and he was looking at a number of things that were kind of in this range on the list. And once we want to get things that are smaller than light itself, light's a wave, so we can see some things that are smaller of the wavelength of light. And there's some funny physics that goes on, so we won't worry too much about the details. But things that are much smaller than the light, we won't be able to see because it's smaller than the light we're trying to observe it with. So things like coronavirus, we can just barely image viruses using light. Can anyone think of any other techniques, either with things higher up the list or other types of microscopes you've heard of that we can look at things smaller than we can see with light?
Scanning electron microscopes.
Oh, electron microscopes. Okay, so we can use electrons, and electrons can be considered a particle or a wave, but they can get smaller than visible light. And if we look at X-rays, you might have also heard of a technique called X-ray crystallography. And that's good for taking pictures of some things, including viruses if they're frozen in a crystal structure. But what might be the problem that we encounter a lot of the time trying to look at things with X-rays? Like what would happen if I tried to look at, say, the fibers on jeans with X-rays? Would I be able to see something closer than Alex could magnify? X-rays, like if you have an X-ray, when might you have an X-ray of your body? Has anyone ever had an X-ray?
Yeah. You would
Yeah.
see just your bones.
You can see just your bones. And why can you see just your bones?
Because your bones are.
Because your bones are harder than the rest of your material, the material of your body, and the X-rays can go straight through the rest of it. And so if we try and look at things with X-rays, the problem is if we look at small things, the X-rays will go right through small things. So we get to the idea of electron microscopes, because electrons we can get to be even smaller. And there's an interesting thing, and I'm going to turn off this screen share just a sec to, well, no, turn it off fully to show you what we're going to do to model imaging things with smaller things. So we're going to use a technique making the shadow of something. So similar to when you have an X-ray of your bones, you'll see a shadow left behind of where the X-ray blocked the bones but went through the flesh. And we're going to try and take shadows of regular objects. So I'm going to show the setup here. I tried to show a setup with a different camera before I got things set up, but my bandwidth wasn't working, so we're stuck just with like a single camera here. So I'm just going to reposition this. And I've got a tray to contain the mess I get. I'm going to grab a piece of paper, and I'm going to, oh, I should have cut that ahead of time. I'm going to grab a piece of paper that fits into the tray. And I'm going to take an object that's a fairly medium size, like a key. And we saw a key on that list. And now I'm going to try and bombard it. So I'm going to bombard it with particles. And if we imagine these are low energy electrons, they'll have a fairly big size. So I'm just going to drop a bunch of electrons. And I'm going to look at the shadow left behind once the object's gone. And I'm going to bombard enough that the surface is relatively covered. And now when I remove, and we see that coin is on the key, so that key was blocked. And we have an impression left behind, and we know that something was there, but we can't really see any useful detail. And the reason for that is because what we were trying to observe, in this case the key, wasn't much bigger than what we're trying to observe with, so the resolution of our image ended up being awful. Now if we try bombarding it with something smaller, so I'm going to remove these coins. And I'm going to take the same key, and I'm going to bombard it with grains of rice. So bombarding with grains of rice. And then when I remove the object I was bombarding, we see the shadow of it left behind, and that shadow ends up being a lot more in the shape of a key, and it's just missing the fine details like the teeth of the key. And then we'd need to move to something even finer. Like in this case, I'm going to use wheat flour that's ground, and the particle size of flour is even smaller, so I'll get a better image of the key with that. Now what I want to ask all of you to do, and hopefully you understood this method well enough to try it on your own, I want you to pick an object that'll be a mystery object for us. Have your camera not showing the object at all, bombard it, take the object away, then move your camera onto the shadow, show us the shadow, and we want to try and guess what you took an image of. Did that technique make sense to you guys?
Yeah.
Perfect. So if you've understood that, start bombarding. When you're ready, just shout out, and I'll spotlight your video, and we'll see if we can guess what you were taking an image of there. Okay, and if anyone's ready to show their shadow, then let me know and I'll spotlight your video and we'll try and guess what you bombarded.
I think we're ready.
Excellent. So I'm going to spotlight your camera. Okay, we have you spotlit. So anyone either with your microphone or in the chat, try and guess what we're looking at, the shadow of there.
A spoon.
So someone thinks a spoon. Let's hear some other guesses.
A pen.
I was thinking maybe a pen as well. And it's a pen. Perfect. Okay. Thank you for sharing that one. Just going to unspotlight you. Do we have someone else who wants to share theirs? Looks like some people are busy getting things ready. Give a little bit more time when you're doing that. I'm going to show one that I did, and this is one where it's not that good of a resolution because the object I was looking at is not that much bigger than what I'm looking at. So I'll show you with this one, and if no one can get it from this image, then I'm going to switch to my finer powder, which is flour, and it should be a lot more clear from that. So any guesses on this one?
Scissors.
Excellent, scissors. And that's good you managed to guess that. Well done. Okay, and after the time to guess mine, does anyone else have theirs ready for us to attempt to guess?
Yeah, I've done mine with flour. It's kind of like really easy, but hey.
Okay, and flour will generally make things easy, and that's something I want you guys to get an appreciation for because the particle size is pretty small.
Can you see it?
Yes, it looks very clear. Does anyone want to guess what we think that is?
Spoon. That's a spoon.
Yeah, that's fun.
Perfect. Thanks, Alex. And an interesting one to try the difference of is the difference between a spoon and a fork, because the fine detail of the prongs of the fork will make a big difference. Does anyone else have one that they want to show before we move on to the next experiment? It looks like Deanne, Rose, and her friends are busy trying to do something. Do you girls have anything you want to try and show and have us guess? This was to model how if we're using smaller and smaller particles. You ready? Okay, so I'll spotlight your video and we're going to try and guess what you have there. So your video's spotlit.
Here, I don't know if you can see it.
And it looks like a mix of.
Like here.
Spoon.
Is,
Spoon.
so someone guessed spoon. Is that correct?
No, like it's not very well done, but like sort of.
I'm not sure. Are there any other guesses what we're looking at?
Is it a pencil?
Almost.
A
So a
pen?
pen?
Yeah, it's a pen.
Okay. Okay, thank you, girls. So I'm going to unspotlight you now.
Big pen.
Okay, so now moving on to the last experiment. So if we get to smaller and smaller things, and a kind of neat trick of physics, which comes from the wave-particle duality, and I won't go into detail what the wave-particle duality is, other than to say things like protons and electrons can behave sometimes like a wave, sometimes like a particle. And the more energy they have, the faster they're moving, the shorter their wavelength. So by adding energy to things and accelerating them, like accelerating electrons in an electron microscope, or like accelerating protons or alpha particles, or anything else in a particle accelerator, the more energy we get, the smaller it appears, the higher resolution we're able to get. So we're going to very quickly try and model the Rutherford Gold-Foil experiment, which proved that atoms have a nucleus and was able to calculate with a surprising level of precision the size of that nucleus. So I'd asked you to try and print out a couple of pages like this. We're going to pick one page to start with. It'll be slightly easier using the bigger dots. So I'm going to say, go to the page with the big dots. Yeah, I guess I only have the big dots that are close together. I used all the big dots that are small apart for mine. And what we're going to do, we're going to model bombarding this with alpha particles. The Rutherford Gold-Foil experiment, he took a really thin sheet of gold and he bombarded it with particles, alpha particles, which are the nucleus of a helium atom. And then he counted the number that bounced back because they hit a nucleus and the number that went through. And from that was able to calculate the size of each of the nuclei. So these circles are representing the nuclei of a gold atom. Of course, not to scale. The separation would be a lot bigger if it were to scale, but the activity would be a lot harder. And what we're going to do is we're just going to take a pen or pencil. In my case, I'm going to take a marker so you can see it better because I want you to be able to see what's on my screen. And I'm just going to have this sheet on the table. I'm going to uncap the marker and drop it from a couple centimeters above. So I'm not aiming at any particular square. It's going to hit a random place on the page. And in this case, we have 2 marks. You should be able to see 2 marks there that the marker made. And not having hit a nucleus, that alpha particle would have gone through. Then I'm going to simulate that again. So dropping it again, we have another alpha particle that would have gone through. And I'm going to drop that again. It missed again. There, I have some from alpha particles that would have bounced back as they hit a nucleus. And I'm going to repeat this until I have about 20 dots on the page. And I noticed with a marker, because it bounces, I'm getting multiple dots, which isn't great. I'm going to count each multiple of a dot as a dot because it's equally likely that those will happen inside and outside. It doesn't affect the quality of the results. And I'm just going to repeat this till I have at least 20 results, maybe a bit more. And I want you following at home to do the same thing. So take the sheet like this, maybe use a pen or a pencil rather than a marker, and just drop it a bunch of times until you have 20 or more dots. And we're going to use that to be able to calculate the size of these dots on the page. If anyone doesn't understand what I'm asking you to do, please ask now. If you understand, I'm assuming that, like, if I don't hear from you, I'm assuming that you're getting a bunch of dots and that you'll be ready to share your results momentarily. Once you've done it a bunch of times, either do it even more times if you're eager, or if you stop, then you need to count the number of dots that are within the circles on the total number of dots. And we're going to use those in just a moment.
I've got 7 out of 20 hit a dot.
Excellent. 7 out of 20 hit, and I've got 13 out of 27. And I'm going to give you guys a link to try and enter your results. If the link doesn't work for you, then just add it to the chat, and we'll get the results that way. Hopefully, we get results from a couple of people. It's okay if some people didn't understand or didn't get enough results, but that link will open up a Google form, and I'm going to share my screen just so to show you how to use these results, and then our calculations will happen quite quickly once we have everyone's results. So sharing my screen again. With that link, you'll have
we didn't get the link to it.
You gave the wrong link, Michael Gregory. It didn't copy. You gave the magnification one again. Was that trying to?
Thank you. Okay. This should give. Nope, that's the wrong. Okay, that should give a link to the same one I have on my page. And,
yeah, that's it.
And call this paper paper A, if we were using all the different ones, that would become more useful. So I have 27 dots total on my page, 13 that are within the circles, and I've submitted that result. Hopefully a couple of you will submit your results too, so then we'll see the results pop up on this page. So we see mine already. Excellent. We have another set of results. And we can have that automatically calculating as we go through. So we see in mine, the proportion of the area that was hit was 48%. Here, I think that was Alex's result. We have 35%. The area of the paper, the area of an A4 sheet of paper is roughly 600 square centimeters. The area of each of the dots we get just by multiplying both of those by each other. So here the total area of dots on my page is 288 square centimeters. On Alex's 210. Hopefully we get another set of results or two because the quality results gets better with that. The number of dots on the page, this page just has 7 dots by 12, so 48 dots.
16 out of 35.
15 out of 35?
16.
16 out of 35? Okay, so we'll add that to the results if you're not able to. Are you able to use the form to add it?
What?
Yeah, the form that I gave the link to. And so the area per dot, if we divide the total area by the number of dots, we have the area that should be taken up by each dot, like the cross-sectional area of each dot, And then we can divide that by pi and take the square root, and then we'll get the diameter of each dot. For some reason, the column ran out here. But if we do that, it works out in this case, for mine, the calculation, I don't think it's showing for you guys, but it works out to 1.8 centimeters it should be across. For this second result, it's working out to about 1.6. And if we try and measure that, then we see it should actually be, that's surprisingly close for one of them. It's 1.7. And we managed to measure that, like 1.7, kind of awkward to see. But our measurement was done not with taking a ruler, because if we're looking at something like an atom or something smaller than light, we can't take measurements just with a ruler or by getting something small, putting it near, but it's by this method of bombarding. So like this experiment was to model the experiment that historically was used to measure the size of a gold nucleus and to prove that nuclei existed. Are there questions on that experiment?
Could you put the equation in the chat?
Oh, yeah, of course. So is that once you have the area of the circle, like what we had to the last column on the spreadsheet?
How you do it, like from the number of dots and all of that. So you make an average, and then
yeah. So I'm just trying to think of whether to go forwards or backwards in the chat. So to go backwards, the last one is area equals pi r squared, just area of a circle.
yeah.
And so once we had the area of each circle, the area of one circle equals total area of circles, like for the whole page, divided by number of circles. So that like that's in the chat too. And then the total area of circles equals proportion of circles. So that was like your, in my case, it was 13 out of 27. And the 600, that's the area of the page. And then the proportion of circles is number of dots in circle divided by total number of dots. Does that make sense, all of those steps?
Okay, yeah.
So like you can do it for each individual result, or if we had like all of the results together, we could total them.
Yeah, you can make an average. Yeah.
Exactly. And I won't take the time to do that because we've gone a little bit over time. So I think I'll wrap things up there. But like if you end up trying the calculations and if you want more advice on it, just get in touch and I'm happy to help more with that. And this experiment, to model the Rutherford experiment, like with these sheets, this is from a professor at the University of Valencia in Spain called Chantal Roca. And she has a great set of experiments. Those of you who joined me for like the electrostatics camp back in the springtime might remember some of the ones that I showed that she'd done, but it's a great project. So it's like always fun to get to show those sets of experiments. Okay, with that, I think I'm going to wrap up. If you have extra questions, I'm happy to stay on a couple minutes afterwards. But since we've already gone over time, I want to thank everyone for coming. I want to remind you of the upcoming camps. So on Tuesday, there's a lecture on the Big Bang and the evolution of the universe from the Joint Institute of Nuclear Research, Dmitry Dryablov. I'm really looking forward to that one. Next Saturday is on electromagnetics. So hopefully you'll be able to get some wires, batteries, things like that for that. And a couple more ones coming up on the schedule. So hopefully I'll see you guys soon. Thanks again for joining. Remember to stay curious. Have a good evening.
Michael, thank you.